All right. Yeah, thanks, Arthur. Yeah, thanks for being here. I'll be talking about this paper, Efficiently Provable Approximations for Non-Polynomial Functions. This is joint work with Shravan, Dimitrios, and Babis. And this was done when all of us were at Lagrange. So this title has essentially three parts. Right? It has the efficiently provable part, has an approximations, and the non-polynomial functions. I'll sort of walk through these one by one, eventually in some order. Right? So starting with the provable part, something you may have seen before. So what are proof systems or snarks? So you have a prover, you have a verifier, and the prover wants to prove something to the verifier. Wants to say that, okay, this statement is true, or that I know a witness has said this statement is true. And so there's a statement, there's a witness, and the prover sends a proof to the verifier looks at it and then decides, am I going to accept, am I going to reject? And we want these standard properties of completeness, soundness, and succinctness. Completeness says if the prover follows the protocol, verifier accepts. Soundness goes the other direction and says if the verifier accepts, the statement must be true, which is the, I guess, the harder property to prove usually. And succinctness basically makes things non-trivial, where you want the proof size and verifier time to be actually succinct. So in practice, we often have a sort of a split between the front end and the back end of a proof system. The front end is the part that sort of you write. You describe what is the statement I want to prove, and it's going to convert that into some form that the crypto can use. So you might have intermediate representations like R1CS, Plonkish, AIR, etc. And the back end is the crypto part, which takes this arithmetization and then decides to give you a proof at the end of it. And this talk is mostly going to be focused on the front end part. And we're basically telling you how do you make better circuits. So, well, some applications, there are a lot more than these. And I've picked these for a specific purpose. I'll explain why. So you might want to prove things or verify that certain computations have been done correctly. You know, things like machine learning, a bunch of DeFi things. And you want to verify that these things are done correctly. You want accuracy. So two of those things are important, right? And these applications can be split into sort of two parts. One is sort of simple operations like additions, multiplications, low-degree polynomials, things like that. And these are efficient. You can do them nicely inside a proof system. And there is this non-polynomial part, things like exponential functions, things like sigmoids, or let's say sine and cosine. These are hard to do. And primarily because they use real number arithmetic. And proof systems are not very happy with real numbers, in a sense. So this causes a problem, right? Because proof systems are sort of mainly working with finite fields. And we need to figure out how do you encode a real number into a finite field. And yeah, the problem is that because the non-polynomial functions require you to compute with real numbers, you cannot sort of express them as field elements without losing some information. A real number has, I guess, infinite amount of information in it. And you need to sort of encode somehow. And two ways to do this is you either have a fixed point encoding or a floating point encoding. For the purpose of this talk, I'll be focusing mostly on the fixed point. And there have been a lot of work, a lot of papers and et cetera done on floating point encodings for snarks and how to prove them, how to prove sort of floating point operations done correctly, but they still end up being slower than fixed points. And it does turn out that fixed points can actually achieve as much accuracy, if not more. And feel free to talk to me later about why. So, well, what is a fixed point encoding? It basically says, okay, give me a scaling factor or a number, and that's going to determine how many bits I store. So if you have a real number, just cut it off at some point and then say, okay, this is my approximate real number now. So what that looks like is you have a range min to max, and you try to map it to a smaller range of integers. And that can then be mapped into a field. And then the operations on these, because you're just multiplying them by a number, become fairly simple. You just have to add things to add the real numbers. But multiplication is slightly more annoying because what happens when you multiply, say, two numbers, right? Maybe you start with like 166 and 307, and the actual product of these two numbers becomes significantly larger than what you expect because it's been multiplied by the scaling factor twice. So you end up having to sort of divide by the scaling factor that you multiplied with to sort of rescale or truncate this number once you compute a fixed point number. And this truncation step has two problems. One is it makes your prover time slow inside your circuit. The other thing is it loses accuracy. Because you're truncating, you do lose some information each time you do this. So you sort of accumulate errors with each multiplication, and the goal is, can you reduce this accumulation of errors? So the goal of this entire paper is, now that I defined sort of some notion of what the title was, can you prove that, let's say your output of a non-polynomial function is approximately correct with sort of low prover overhead. You don't want the prover to do too much work. And also low error. You want this approximation to be actually pretty good, right? So, well, before we sort of go into the techniques, I'll just talk about what we get. So we show that, yes, there are many existing ways to do this, and we sort of improve on them in one axis or the other. So we have one approximation that it's Paddy approximants. These are sort of drop-in replacements for like polynomial approximations that people do. And these are sort of for free, just replace it wherever you want, and this sort of focuses on the proving time aspect and says, okay, you can get much better proving time for almost no loss, right? And the other thing is this notion of quadrature-based or numerical integration-based approximations. And this says that, you don't sort of do more multiplications as you want to increase your accuracy. I'll explain why I explain why multiplications matter, but I'll explain how this happens later. And this is focused on the accuracy side of things. So how can you decrease the error in your approximations as much as possible? And using both these techniques, we just illustrate some high accuracy requirement applications, and then we say that, okay, things like orbital mechanics. You want to know if an asteroid is going to hit you tomorrow or like 10 years in the future. Or things like token pricing. You want to make sure that you don't have errors in, say, your last bit. And we show that you can get up to 64 times roll error. So for the purpose of this talk, I'm going to use this as sort of the running example. This is the sigmoid function. It's a nonlinear function that's used a lot in machine learning and a bunch of other places. And what are sort of existing ways to approximate these things? Right? So one simple way to do this is, well, divide your function that looks like a curve into a bunch of linear pieces. You use more pieces, you get more accuracy. You can also do a polynomial approximation. You use a Taylor series, and this is good close to 0 or close to the point that you pick, and it becomes worse the further away you go. Or you can have a lookup table. Just take every input and get every output. But all of these have their own sort of issues as you need more accuracy. So the piecewise linear, well, if you want more accuracy, you need more pieces. And proving that this thing is being done correctly requires lots of if and else cases. You need to see that, oh, is my input in this region, then I need to use this linear piece, and so on. And Taylor series have their own issues, where if you want more accuracy, you need a higher degree of the polynomial that you're approximating with. And this requires computing a lot of powers inside your circuit, which requires more multiplications, and hence more errors. Lookup tables have just the problem of, well, if I need more accuracy, I need a massive table. So the table just becomes larger and larger, and your proving time scales that badly. Right? So, this is what happens when you try increasing the accuracy. And the goal is to avoid sort of this blow up of something, either the error or the proving time as you try to increase the accuracy. So our first result is following from this is, let's say you just have your polynomial approximation, which is this T6 of x. Let's say this is the Taylor series for the sigmoid function. And what we show is you have a rational function approximation, this R33 of x, that basically does exactly the same or has the same error as the Taylor series, but note that it only has terms up to x to the power 3. So you do fewer multiplications, you still get the same accuracy. So it's a very simple sort of drop-in replacement. You lose nothing, you just get much faster proving. But unfortunately, notice that if you need more accuracy, you still have to increase the degree of the polynomial. You still need to increase the number of terms you have, and this still increases the number of multiplications. So the second part of this talk is going to be, well, how do you avoid increasing multiplications? Or when you increase the accuracy you want, can you avoid increasing the multiplicative number of terms? So let's start with this observation. Let's say you have y sigma of x, and just solve for this in terms of x. So you can write x as a natural logarithm of something. And there's a nice property of the natural logarithm, which is you can notice that log y is basically the integral of 1 by y, which in some sense, you're basically converting looking at a nonlinear function, log y, to something that is almost linear or sort of just has 1 by y. You just have a y in the denominator. It's not linear, but you can still compute things about it because divisions are as easy as multiplications inside proof systems because you can verify them rather than prove them. So based on this, we know that we can approximate integrals. We have lots of techniques. Just the definition of the integral is basically, let's have a lot of rectangles and then sum them up to become your integral. And basically what this says is you can replace an integral by a summation. So you can, this one example is Gauss-Legendre quadrature. Basically says that, okay, I have an integral. I can replace this by a summation of n terms at pre-computed points and predefined weights. And the good thing here is, notice that as you want to increase the your accuracy of your approximation, all you have to do is increase the number of terms in the summation. This does not increase the number of multiplications that you're doing iteratively. So just a sort of worked out example is, you start from the sigmoid function, and you end up with some function or some approximation that looks like something like this. So you just check this equation inside your circuit. X is approximately equal to the summation that depends on y on the right-hand side. Note that, even because I'm defining the equation like this, you can't actually write y as, let's say, a polynomial function of x. There is no sort of nice equation, unfortunately. So clearly, this helps just because we can have a summation instead of a product of things. So as you increase the number of accuracy, you just add more terms here, and you're fine. So this, of course, I just showed an example for sigmoid. Does this example generalize? It sort of does. And the property really is, does the function inverse, like exponential to log, or like sine to sine inverse, does it have a nice derivative that you can work with? And it turns out most of the nonlinear functions we actually care about do have this property. And because of that, you can get expansions of like integrals that look like this. And these also interestingly work for things like functions that you don't even have actual representations for, like the error function or the Lambert W function, things like that, where you can't actually write down what their function is in some elementary terms. You just write them in terms of an integral. And we're able to prove those functions as well. So here's sort of a comparison. This is a hard thing to do just because of the number of axes we have. We have 3 axes instead of 2. And it turns out we have an expressiveness axis, which is, I'm defining the size of the circle, which really says, how many functions can I apply this for? Can I apply this for all functions? Can I apply this for some functions, or like very few functions? And then there's a standard thing like accuracy on the y-axis and performance on the x-axis. So this is where our approximations are in this space. Depends on what your trade-off between accuracy and performance is. You can choose whatever you want. Right? The Paddy approximations are basically the best in performance and about as good in accuracy as Taylor series. But we show that our quadrature thing basically gets almost the best accuracy you can without sort of losing completely on the prover time. Because as you sort of scale up, the lookup tables become extremely large and you just become infeasible to prove, while this still scales up very well to like very large scaling factors. So some applications that I just want to wrap up with are things like the Bancor protocol, which sort of helps you do automated token pricing. And specifically, why is this nonlinear is because there's this fractional ratio in the exponent. And this makes it so you cannot compute things like x to the power 2.3 or like 0.7. This is not something you can easily write as an expression. And this is where our techniques help. I'll explain how it works in the next slide. And also, instead of having constant product or constant sum pricing curves, you can have more complicated curves in Uniswap v4. You can have things like weighted product curves or Lambert curves, which are very hard to express and, let's say, prove things about in smart contracts. And for this, we still show, okay, our approximations are still pretty good. And we also have some other examples of somewhat slightly out there things, like orbital mechanics, just to calculate trajectories of celestial bodies, or things like nonlinear layers in machine learning. So just to dive into this a little bit more, so why is this a hard thing to do? Is specifically because this fraction f is actually a fraction. It's not an integer. So computing this formula inside a smart contract becomes hard because you don't even have floating points support. You have to use fixed points inside smart contracts. And instead of computing it, you could maybe have a prover compute it outside and then verify that the computation is done correctly inside a smart contract. So what would you like to prove? You would like to prove something like, given these bunch of things, and I pay E tokens, or E reserve, and I'm going to get T output tokens. And these have been computed correctly according to whatever pricing function was in this slide. Right? And how do we prove things like y is x to the power k? This sort of boils down back to our exponential things, because y equal to x to the power k is the same as writing log y is k log x. And given this, you can just expand it on both sides using integrals and then approximate it, and it works out fine. So one sort of nice thing here is that you're basically converting exponentials to multiplications and multiplications to additions, which makes it a lot easier to prove things about them. And this gets much better error performance than previous work that we had. So this is a summary. We present these two approximation techniques for a large class of non-polynomial functions, which are efficiently provable and scale well with accuracy. And you have additive terms instead of multiplicative terms, which So you're trading multiplication for addition, essentially, which is a lot better. And we obtain up to 256x better errors than comparable baselines for these functions. And this will be at Usenix Security in a few weeks. And that's the paper. Thank you.
All right, thank you very much. Any questions?
Hey, thanks. Yeah, that was a cool talk. So I think I wanted to ask about, so it looked like most of the things you were showing were maybe intended for sort of like pre-built or pre-compiled circuits. I wonder if you think that there's a possibility for snarks that sort of compile from high-level languages to adopt this approach, or what the possibilities are there.
Yeah, so I think it depends on, so let's say you need to know what the function is before you start applying these formulas because you need some properties of the function, right? So you need to know that you can write them as nice integrals and things like that. So you don't need to pre-compute some things about the function itself, but the input is of course not, you don't need to know the input. So let's say you have a list of functions that you care about and you know that some of them are going to be appearing, and let's say you just predefine how to do those functions as gadgets, and then you can use those gadgets.
Thank you.
Very good. Any further questions?
Can you go back to the slide with the graph? Oh, just passed.
Yep.
So here, is the proving time axis like it gets less as I go to the right, or it gets more?
Yeah, okay. Basically, I wanted better or good to be the right side and bad to be the left side.
Okay, good.
Yeah, so and the same for accuracy. So as you go up, you get better accuracy, and on the proving time, you get lesser proving time as you go right. So
okay. Thanks, that answers the question. Thanks.
Perfect. Any further questions? I have a small one. So for an application designer, what is kind of like your recommendations regarding the error boundaries?
So it depends. So you need to fix one thing. So if you're using a fixed point approximation, you need to fix what your scaling factor is or your quantization domain is. So that tells you how many bits of accuracy you can even hope to get. So let's say you have 120 bits of potential accuracy. And what we will tell you is that, okay, once you fix that number of bits, we can tell you, okay, you're going to lose the last 4 bits or the last 3 bits. And so you can trust all the values up to the last 3 bits.
Cool. Thank you so much.